I'm Padioplasma, and I'm a physicist, PhD physicist. And a couple of years ago, a friend of mine, Cody Cassidy, who I'd known since he was a child, because I was the senior scientist at a publishing company called Klutz Press. And Klutz Press writes books for teenagers with lots of hands-on tools in them. Mirrors and microscopes and telescopes and thermal indicator paper. I was the one that had to come up with activities for those books. And John Cassidy was the president of that publishing company, and Cody Cassidy was one of his sons. Well, it turns out Cody grew up and became a really funny writer. And I'm more of a stand-up voice comedian and lecturer, whereas Cody is a written word humorist and writer. So he came to me with this idea for a book, saying, I think we could do a book about the science behind the world's most interesting ways to die. And I thought, oh, dear me. But it turned out we managed to get an agent for our book, and the agent arranged a bidding war among publishers. And the bidding war was won by a very good publisher, Penguin. I'm very impressed by them. And so we signed with Penguin and began writing. And one thing I learned was that you just have to keep writing. A book is a huge amount of work. I've done a dozen of them. And so Cody and I worked all the time over a couple-year period and eventually came out with this book, which is doing well. It's already in its third printing, so that always says good things. Okay. So the first story in the book is what would happen if you're in an airplane and your airplane window popped out. And what we like to do in the book was to find actual cases where this happened. And in this case, oh, by the way, the slides often have text on them, just in case people can't hear the voice. So you may get a lot out of this with text. So not only did the window pop out of this airplane, it was the pilot's window that popped out. And Captain Tim Lancaster, when the window popped out, all the air in the airplane rushed out of that window. And I was able to go to, and I found an online site that allowed me, by specifying the size of a window and the pressure difference between the inside of the airplane and the outside of the airplane, as you go up in altitude, the pressure decreases, to find the speed of the air that would rush out the window if it popped out of an airplane. And the speed came out around 300 miles an hour. And those sorts of winds are the highest winds ever recorded on the surface of the Earth in the middle of a devastating tornado. So that wind blowing out of the airplane, out the front window, actually grabbed the pilot, pulled him out of his seatbelt. He had taken off his shoulder harness and pulled him out the window. But his legs caught on the steering wheel or the yoke, and he didn't go shooting all the way out. And one of the flight attendants grabbed him and held on for life or death while the co-pilot tried to bring the plane down. And one of the problems the co-pilot was having was the air rushing in the window was so loud he couldn't hear what the air traffic control people were telling him. So this is called explosive decompression. And in the bottom right, you can actually see a picture of the pilot, a few days later in the hospital. He and the flight attendant in the multi-hundred-mile-an-hour wind outside the airplane and -1 Fahrenheit temperatures did experience some frostbite. In fact, the flight attendant had a frost-bitten eyeball, but completely recovered. Now, the thing is, within a few months, the pilot was back flying again, but the flight attendant quit flying forever. The flight attendant said this, I knew I wouldn't be able to face his family, handing them a matchbox and saying, this is what's left of your husband. If we'd let go of his body, it might have got jammed in a wing or gone into the engines. So that's hard to handle. So, I've actually undergone explosive decompression training, and I can tell you what happens if a window pops out of an airplane at altitude. And here, this is a chamber that they put you in, and then they explosively decompress the chamber. They attach it to a large vacuum chamber. And this was actually done in, yeah, that flight attendant really deserves a raise. This was actually done on Mythbusters. And Jamie actually wore a pressure suit into the chamber, and they explosively decompressed it. And what happens if you're on an airplane and this happens is that if you're not wearing a pressure suit, all the air inside your body comes out. You fart, you belch, all the air just bursts out, and that air is very rich in moisture. And because it's expanding, the air cools, it's called adiabatic expansion, and the moisture condenses. So if a window pops out of an airplane, it immediately becomes full of a cloud. And people in the airplane that this has happened to almost always report they thought there was an explosion because there's a loud boom when the window blows out, and that this was smoke from the explosion. But actually, it's just a cloud. Yeah, so moist farts that then condense.
Hello, everybody.
Now, at altitude, this pressure suit that Jamie is wearing is for U-2 pilots, and the U-2 flies above 60,000 feet. And at those altitudes, the pressure is so low that water boils at body temperature. So here's a picture of Jamie, and there's a water bottle in the foreground. And this water bottle in the foreground is boiling at room temperature. And so it turns out that without the pressure of the atmosphere pushing down on that liquid, even room temperature or certainly body temperature can make the water burst into boiling. And this is a very bad thing. Now, most aircraft fly at 45,000 feet or below. And so at those altitudes, the pressure is not low enough to have it burst into boiling. But at those altitudes, with there's so little oxygen, you'd be dead in 4 minutes. The pilot or co-pilot dives for the ground, gets you down below 10,000 feet where you can continue to live, even if the oxygen masks don't deploy. You know how they always say, in case of loss of cabin pressure incident, oxygen masks will drop down from above. Put them over your nose and mouth and breathe normally. Right. You got to breathe normally after this explosive noise and the cockpit or the aircraft full of cloud. Yeah, the Concorde was up there at very high altitude. It takes about 15 seconds for if you go into explosive decompression, or as we know from 2001, A Space Odyssey, it takes about 15 seconds before the blood in your body actually boils. Chemists know this because they put boiling beads into liquids that they want to boil that have scratches and air pockets in the boiling beads. And this allows the boiling to start gently and evenly, whereas without any starting bubbles, liquids burst into boiling. They superheat and burst into boiling. Inside your body, there are no air voids in your blood. So it takes a while for the boiling to get started. So you have 15 seconds, and the aircraft has 15 seconds to dive down and get to a lower altitude. And by the way, your body does not detect the oxygen level in the air you're breathing. It only detects the buildup of carbon dioxide. And that if you're at a high altitude and there's not enough oxygen to keep you alive, you're breathing out the carbon dioxide. So you have no indication that you don't have enough oxygen. And you just gently drift off without noticing at all into unconsciousness. I know because in my training for I was drafted in the Air Force during the Vietnam War, and I got the explosive decompression training. And in that training, they have you sit and write your name over and over on a piece of paper, and you pass out. You don't even know it. And when I had woke up again, when they brought the air back to the airplane, I had written my name several more times on the piece of paper that I remembered, because it takes a while and it takes oxygen to help your memory work. Yeah. Okay, so in fact, at the atmospheric pressure at the surface of Mars is like the atmospheric pressure on Earth at an altitude of 100,000 feet. And this of course was portrayed in the Hollywood movie Total Recall, where Arnold Schwarzenegger is showing what would happen if you were out on the surface of Mars with this very low pressure. The blood in your body would boil, and you would expand like a plumped sausage. So this has happened to people on Earth, and where they were working in a vacuum environment in a spacesuit, and the spacesuit leaked, and most of them, all but one, as far as I know, were rescued within 4 minutes and recovered. But one of them was in the vacuum for 10 minutes. And okay, and another accident that happened was on this Aloha Airlines flight. It turns out the entire top of the aircraft blew off, and this was because the Boeing 737 is rated for 30,000 takeoffs and landings, because every time it takes off and goes to high altitude, the inside of the plane is pressurized and stretches the metal outward, and when it lands, it's compressed back again. And this aircraft had actually gone through 90,000 flights. It's 3 times as many flights as it was supposed to go through. And but it turned out, even losing the top of the aircraft in this large blow-off, none of the passengers were killed. They were all still, they had their seatbelts on, and that's a good reason to wear your seatbelt in an airplane. Only one flight attendant was blown out of the airplane and was never recovered. Okay, so one of the so that was actually might happen. So I wondered, as part of this book, whether magnetism could ever kill you, and so I did my research. So, for example, the magnetic field that you've grown up with your entire life is measured in a unit called the Tesla, and Earth's magnetic field is 50 microteslas. It gets weaker and stronger at times, but it's pretty weak. And although pigeons and migrating sea turtles can sense the changes in this Earth's magnetic field and use it to navigate, it doesn't appear that humans can even sense this, let alone be affected by it. Now, one of my students, Chris Thrush, worked at General Motors after he left my university, and he was on the team that invented these new magnets. They're called Neodymium-Iron-Boron Magnets, and they are 10 times stronger than the strongest World War II level magnets per unit mass. When you get this strong a magnet, you can discover some interesting things about it. Here, the magnets are being used to push grapes. It turns out if you bring the north pole of one of these neodymium magnets near a grape, it will repel the grape. The amazing thing is the south pole of the magnet, the other end of the magnet, also repels the grape. Just like both poles of a magnet attract iron, both poles of the magnet repel grapes. And it's just that this force of repulsion is 10,000 to 100,000 times weaker than the attraction for iron. So that's why you never knew that grapes are repelled by magnets. Now, it turns out that the grapes are full of water, and water has this property called diamagnetism, which means it's repelled. And it turns out these magnets, those of you that might have used them, they're so strong they can really pinch your hand. In fact, I have had flesh ripped off my body by getting two of these magnets too close together near my hand. And I was going to write a book for Klutz Press with strong magnets for children. But luckily, before I wrote the book, I found out that several children had died by eating these magnets. And it turned out the magnets themselves are non-toxic. You can eat one of these magnets, it'll pass right through you and do no damage. But what they had done was they had eaten two of these small magnets, and the two small magnets had been going through their intestines, and the one magnet on one side of the intestinal bend and the other magnet on the other side of the intestinal bend pulled together so strongly they cut a hole in their intestines. So I never wrote that book because I'm very concerned when I'm writing science books for children to make them safe, because if any child actually does get injured or dies as the result of my book, I would feel terrible, and the entire publishing house would probably go out of business. So being a scientist, being a senior scientist, is a serious job. You have to keep up with all the latest in science, and you have to be creative and have fun too. Of course, the biggest magnetic fields you ever encounter are in an MRI, and they're 10,000 times stronger than the Earth's magnetic field. They might be 1 or 2 Teslas. And those magnetic fields are so strong, if there's anything made of iron in the room with the MRI, it will be attracted to the MRI. And luckily, in this case, no one was injured. But there have been cases where steel oxygen cylinders got sucked into the MRI while there was a patient inside there, and that was not good. When the magnetic field gets up to 16 Teslas, you can actually fly a frog. So this is a picture of a frog flying inside the throat of a magnet. It didn't hurt him at all. Afterwards, the frog was just fine. If you go to YouTube and you search for the term levitating frog, you can see this movie. In fact, here's a clearer view. So it turns out, just like frogs, humans can be flown in a 16 Tesla magnetic field. But it's never happened because no magnet big enough, with a hole big enough to fly a human, has ever been made. But if one of those were made, I so much believe that this level of magnetic field would not hurt a person that I would volunteer to be the first one to ever fly in a magnetic field. And I think just like those flyaway experiences you can go to around the country where they have a aircraft engine blowing air up that let you fly. You can fly in a magnet if we could ever build one that big and that strong. Oh, that's interesting. So CB indicates he had a guy with a BB in his finger. And of course, BBs are copper-coated steel. And so near an MRI machine, if you have steel implants in your body, luckily most implants are titanium, not steel, you can't go through the MRI machine. So yeah, and any sort of embedded metal is not good in an MRI. That magnetic field is really going to pull on any steel or iron. Okay, so as magnetic fields are applied, the energy levels of electrons going around atoms are changed. And in fact, you can see this in the spectrum. It's called the Zeeman Effect. And the energy level of the electron in the atom goes up and down, and the splitting is proportional to the magnetic field. Oh, that's right. So in Russia, they use iron fillings. Iron is based on steel fillings. And so if you have fillings from other countries, older fillings, you have to watch out for that in an MRI. So here we go. An atom has energy levels. There's the ground state energy level, and this is minus 10.8 electron volts. And then the next excited energy level, minus 6.5 electron volts. And the minus here is relative to electrons outside the atom. So if I give 10.8 electron volts to an electron in this n equals 1 level, I will boost it out of the atom. I'll ionize the atom. And over here, what can happen to an electron in an atom, when I put it in a magnetic field, the Zeeman effect boosts its energy. And by going to a strong enough magnetic field, I could actually remove an electron from the atom. And also the shape of an atom changes in a magnetic field. Every electron itself is a magnet. And in an orbital, there'll be perhaps 2 electrons, one spin up and one spin down. And if you go take to even 100,000 Tesla, now this level of 100,000 Tesla is so strong, you just don't encounter that in reality on Earth. But we can hypothesize, we can predict what would happen, that atoms, instead of being spherical, would be stretched into cigar shapes or even lines. So the thing is, out in space, as a neutron star collapses, its magnetic field strength goes up by a factor of 10 billion, 10,000 million. And this magnetic field is so strong that 1,000 kilometers or 600 miles away, you would vaporize as all the bonds holding the molecules in your body broke. All your atoms would then be ionized, and you'd become a human-shaped cloud of ionized plasma. Now, meanwhile, you're near a neutron star, and your cloud of ionized plasma would be rapidly accelerating towards the neutron star. And when it impacted the neutron star, it would be squeezed down to smaller than the size of a red blood cell, and the electrons, by gravity, would be forced back into the nucleus, turning all your protons in your body into neutrons, and you would join the matter of the neutron star. As you fell in, as you impacted the surface, the energy would be released as gamma rays, which would go out through space. Now, these neutron stars, and in particular they're called magnetars, when things fall into them, they emit gamma rays, and they emit very powerful gamma rays. So, for example, in this illustration of our galaxy, here's kind of the location of our sun. And in 2004, gamma rays arrived at the Earth that were powerful enough to actually noticeably ionize the upper Earth's atmosphere. And it turned out those gamma rays came from a neutron star, a magnetar, that was an equal distance on the other side of the center of the galaxy. So these neutron stars with matter falling into them are dangerous beasts. You don't want to be anywhere near them on a galactic scale. In fact, this is a picture towards the center of our galaxy. And near the center of the Milky Way, over here, there's Sagittarius A star. That's how you read this name, Sagittarius A star. And that's the name of the supermassive black hole in the middle of the Milky Way. It's got about 4 million solar masses. And this later picture in 2013 shows the X-rays coming from a magnetar near Sagittarius A star, near the center of the galaxy. And the magnetic fields in these magnetars are 10 to the 8th to 10 to the 11th Teslas. Just astonishingly large magnetic fields. Oh, yeah, so Mademoiselle Bovary, yes, indeed. These kind of signals, the flash of gamma rays and X-rays, or even flash of light, are used by the Vela satellites to watch for nuclear testing. And so we have to really learn about the universe to keep us from killing ourselves. Okay, so humans are very resistant to magnetism and to external electric fields. So there's a kind of weapon called an electromagnetic pulse bomb. And what happens is you make a magnetic field, just like you did in first grade or so when you wrapped a wire around a nail and attached a battery to it and made a magnetic field. But then you make a linear explosive charge that compresses the magnetic field and sends out a blast of much stronger magnetic field. Or you set off a nuclear bomb out in the upper atmosphere. And this electromagnetic pulse, while it does not directly hurt people, it does destroy our electronics. And so that can be a real problem in the everyday modern world where so many things are controlled electronically. And in fact, from a cartoon series, Futurama, this is the statement about humans being resistant to magnetic fields. Funny, isn't it? The human was impervious to our most powerful magnetic fields, yet in the end he succumbed to a harmless sharpened stick. Okay, so death by black hole, and I have to thank Neil deGrasse Tyson, who wrote the book Death by Black Hole, for inspiring this one. And it turns out that usually it's not the fall that kills you. Normally, if you're in free fall, you're just fine until you hit the ground and stop suddenly, and that kills you. But for a black hole, the actual fall itself can kill you. And the reason is it's called the tidal force, is that if you have a mass near the surface of an object that's close to the black hole, over here is the black hole, the gravity force on it is greater than on a mass at the far side. And these red arrows here are meant to illustrate the gravity force on points near the black hole and far from the black hole. And the purple arrow here shows the force of gravity on a point in the center. So all these three objects are falling towards the black hole, but the one in front is being pulled harder than the one behind. So that stretches it apart. And on Earth, we call this the tidal force. The pull of the moon on the Earth stretches the Earth and makes tides. And it also, the points at the top and the bottom are being pulled towards the moon. This is on the Earth, or it could be for the black hole. And this, the result of these being pulled inward, is a squeezing force from top to bottom. So not only are you pulled apart on the line towards the black hole, you're squeezed in perpendicular to it. Now, if you want to fit into a nice tight dress, this is a great thing. So as you fall into a black hole, the effect is called spaghettification. You're stretched out towards the black hole, and you're squeezed in perpendicular to it. And so I think at first that would feel kind of good, you know, that nice little stretching on your back. But eventually the force becomes so strong it pulls you apart. And in fact, I'll tell you how strong that force is. Okay, yeah, so the magnetic force on the human body pushes on you, and the gravity force of the black hole is pulling on you. And the good news is that those forces, you could arrange them to be in opposite directions. They work on every atom in your body independently. So you could overcome some of the attraction of gravity by using magnetic forces. Alas, the magnetic forces also completely ionize your atoms, and so you still become a gas and die. So here's somebody we'll meet later named Phineas Gage, and he used this 1 meter long steel rod. His job as a railroad worker was to tamp down black powder into holes in rocks, and then they'd blow up the rock. But one day, you're supposed to put in the black powder and then put in sand and then tamp it down with this rod. And one day he forgot the sand, and as he was tamping it down, there was a spark, and it blew the rod 80 feet out of the hole, passing through his head. But I only show you this because it was the best picture I could find online of a 1 meter long steel rod. And that 1 meter long steel rod, just to show you how strong the tidal forces are in a black hole, this 1 meter long steel rod would be pulled apart 300 kilometers. That's about 180 miles above a 10 solar mass black hole. So that's one of the reasons people wonder, can I ever lower my camera on a steel wire into a black hole to see what's inside of it and then pull it out? And it turns out the tidal forces near the black hole, a regular multi-solar mass black hole, would rip apart any known substance. So there's no way to lower a camera into a small black hole. However, there are supermassive black holes, and in fact, here we've gone back to the center, a picture of the center of our galaxy, and here's an X-ray picture of the supermassive black hole. It's 4 million solar masses, and it turns out for every solar mass in a black hole, you add 3 kilometers to the radius, and so it's 12 million kilometers in radius. Makes it quite large, and this reduces the tidal effect. So you could actually fall through the event horizon on a supermassive black hole and then find out what's on the inside. But alas, you can never get the information out. It would be your own private knowledge, but because you have to send it out by electromagnetism, and nothing, anything that's traveling at the speed of light or less can never get out of a black hole. So the information can't get out. Okay, so another question that we were asked, or the way we got the questions from the book, we thought of them ourselves, or we talked to our nerd and geek friends like you guys. And one of the questions was, what would happen if you put your head in a particle accelerator beam? And we discovered that the experiment had been done by Anatoly Bugorsky in 1978. He was working on the largest accelerator in Russia, a 76 giga electron volt beam, and evidently their safety precautions in the Russian accelerator weren't as great as they should be. And so he got the beam through his head. And he saw a flash brighter than 1,000 suns, and the side of his body, the beam went through, and it caused his face to swell up after the exposure. And everybody thought he was going to die from the radiation effects, and they sent him off to the hospital, but he recovered, continued on in physics, got his PhD, and worked his career still on this accelerator, although I suspect he was a little more careful. So here's the accelerator. But of course, and by the way, one side of his face, the side of his face that the beam went through, nowadays has no wrinkles because it was paralyzed. It's kind of the same effect that when you get you get the injections, Botox injections. But the other side of his face, having a lifetime of being a physicist and worrying, it's all wrinkled. So if you want to avoid wrinkles, go ahead and stick your head in a particle accelerator. But let's compare the Russian U-70. It's 76 billion electron volts. It comes in one bunch every 10 seconds, and there are 10 to the 13th protons per bunch. The total energy is 20 kilojoules, which is about the energy of a bullet from an elephant gun. Now, what that means, now it turns out most of these protons that went through his head missed everything. I mean, they only hit something if they hit an electron or they hit a nucleus. And so almost all of that energy went right through him and did nothing. The ones that did hit made a spray of other particles and gave him a radiation dose, and that's why he saw that flash of light. But the Large Hadron Collider, the biggest particle accelerator in the world, it's 7,000 giga electron volts. So it's 100 times more energy per beam. The beam actually is like a machine gun. The particles come in 2,808 bunches, 25 nanoseconds apart, and each bunch has 10 to the 11th protons. And the beam itself, each bunch is 30 centimeters long and 1 millimeter wide, and it's traveling at the speed of light minus 7 miles an hour. And this set of the beam itself has 362 megajoules, and that's 5 kilograms at escape velocity. So I'm pretty sure that this is lethal. It's probably even lethal if it hits your hand, and the spray, the resulting spray would of particles would give you a radiation dose that would be lethal. But also, if your hand moved during the course of being hit by the beam, it would be like a saw, and instead of being just a one single hole through you, it's going to be 2,808 little holes side by side. So not good. So don't stick your hand in a particle accelerator. Yeah, he got right back on the horse that bit him. And thanks CB for the Botox. I was just drawing a blank. This accident. So it turned out at the Large Hadron Collider there was an accident in 2008. It turns out they make the magnetic fields that steer their particle beams using superconductors, and there takes a lot of electric current to make a strong magnetic field to steer these particle beams. And one of their superconductors had a bad weld, a bad solder joint equivalent. And so one day, while it was carrying almost 9,000 amps, it it got too warm and became non-superconducting. And so the entire energy of a small city was delivered to this position you see here in the particle accelerator. And this vaporized all the metal around that bad weld, and it pushed multi-ton magnets. But the amazing thing it did was it flooded the tunnel with 6 tons of liquid helium. Now, at the time, according to the laws of the Large Hadron Collider, since this was just a test run, people were allowed in the tunnel. But in fact, for this accident, nobody was in the tunnel because they would have been swamped by a flow of liquid helium, which would not be good. Liquid helium is amazing stuff. It actually, if here's a glass vessel, and it's full of liquid helium. And if you search for superfluid liquid helium on YouTube, you can watch what's happening. And what's happening is, you know, around the edge of a liquid, there's a meniscus. And the meniscus for liquid helium runs up the wall, over the edge, and the liquid helium actually climbs the wall, and here it is as a droplet on the bottom, and it drips off. So in fact, the liquid helium will drop will completely run out of this container. It runs uphill out of containers. It's called a superfluid. If you fell into liquid helium, it would make a boiling layer next to you. I've actually stuck my hand into liquid nitrogen, and it's called the Leidenfrost effect. And it protects you from the cold liquid for a while, but eventually the cold liquid would cool your skin enough it stopped boiling, and it would contact your skin. And if it's liquid helium, it would crawl uphill to coat you. So I think there's a movie waiting to be made here. And of course, if you fell into the liquid helium and you screamed, your voice would be high-pitched, because that's what happens when you breathe helium. So on the liquid helium, the liquid nitrogen too, it's actually used for cells. They can preserve cells, in particular sperm and eggs, can be preserved by cooling them in liquid nitrogen. But they have not been, and there are some frogs that actually freeze until they're solid. We actually did an experiment at the Exploratorium with these frogs. We thawed one out in front of an audience, and it came back to life. So there are organisms that can be completely frozen, but this hasn't been successfully done with complex organisms like rabbits and humans. So I don't plan to have my body stay in liquid nitrogen for any length of time. Okay, so some researchers in Japan decided to measure how slippery were banana peels and other peels as well. And they found out, using a microscope to look at here's the normal peel of the banana with no flaws, and then they squeezed the banana peel and this slippery substance came out. And tribology, by the way, is the study of friction, the effects of friction. And what they were measuring was how low the friction got. So tribology of weeping friction due to a mucopolysaccharide. It's kind of a sugary substance that the banana peel oozes. And they discovered, oh, thanks, CB, by using regular techniques, here they have an acrylic plate and they'd rise it up at an angle and they put a banana on the plate and it stuck there. So it had a friction coefficient of 1.2. And then if they squeezed it a bit, it would start to slide, and the friction coefficient here is down to 0.65. I built a device like this myself to test the friction of rock climbing shoes, and my rock climbing shoes have a coefficient of friction greater than 1, which means I can actually go and stand on a granite slope that's greater than 45 degrees and just stand there and not slip. One of the reasons that banana peels are deadly is that normally when you walk, you stride forward and you actually push forward on that front foot, but the ground pushes back. But if there's a banana peel under your foot, you still push forward, but the floor doesn't push back anymore. The friction isn't there, so you slip. And it turns out the human skull is not designed strong enough to withstand a fall from 6 feet. So if your skull hits the floor from a height of 6 feet, it can crack and you can die. This is Bobby Leach. And in the early 1900s, 1906, I believe, I think we got the date wrong in the book, alas, he went over Niagara Falls in this barrel. And he was the second one. That's right, if you're shorter, you're much more resistant to having your head cracked open if you fall. So he went over Niagara Falls in this barrel, broke both knees and got pretty banged up, but he did survive. The first person to go over Niagara Falls in a barrel was a woman, and she said she would rather be strapped across the mouth of a cannon and have the cannon discharged than go over Niagara Falls in a barrel again. So going over Niagara Falls in a barrel is not recommended. A few people have done it. One person died when he went over in the barrel and he survived the plunge. But here's the deal. If you drop from the height of Niagara onto water, even in a barrel, you'll die. And it's because of the rapid deceleration. It turns out your body stops, but your internal organs keep going, and they rip free from the blood supply and the supporting mechanism, or ribs break and puncture your lungs. But in Niagara Falls, the falling water has churned up the water below and put a lot of air into it. So it's kind of soft water, and you slow down more gradually when you hit the water that's been aerated. And so that's how they could survive. But the one person who died, the other thing that happens is that churning water, it goes around in a circle, and his barrel got caught in an eddy and stayed under the falls for many hours, and there wasn't enough air in the barrel for him to survive that long. So he died from suffocation. But Bobby Leach actually took his barrel around the world and made a living talking about going over Niagara Falls in a barrel. While he was in New Zealand, he slipped on a fruit peel and died. So beware of those fruit peels. They are dangerous. And the friction coefficient of a banana peel is 0.007. That's the friction coefficient is 0.007. The friction coefficient of rubber-soled shoes on wet ice is 0.015. So banana peels are twice as slippery as wet ice. The lowest friction I know of is in the human knee, and the lubricants, the lubricating fluid in the human knee has a coefficient of friction of 0.003. So it is twice as slippery as banana peels. That's right. And so these Japanese physicists were awarded the prestigious Ig Nobel Prize for this work. So we're back to Phineas Gage, and he actually got this 1 meter long iron rod, 1 inch in diameter, that went through his head. People reported he was a jolly guy before this rod went through his head, and afterwards he seemed a bit testy. He seemed to get angry a little bit more often, but I think I can understand that. But one of the weird things is, you probably think that your brain is important, but as my co-writer Cody Cassidy points out, it's your brain that's telling you that the brain is important, so it's probably a bit prejudiced. So on the right-hand side here is an MRI of a normal human brain, and one professor noted that one of his students had quite an enlarged brain cavity. Look at this brain over here. It's quite a bit bigger on the outside than the normal human brain. So he encouraged his student to have an MRI done, and they found out that the student's brain was mostly empty. The black area here is just cerebrospinal fluid. He had a condition called hydrocephaly, which means full of fluid. And he only had 5% of the brain matter of a normal human brain. And yet he had an IQ of 126 and got his degree and graduated. And recently, just in the last couple of weeks, there was an article online of a young child who had the same condition, who seemed to be developing normally, and who only had 2% of a normal human brain capacity. So it's not the bulk of the brain that matters, it's where it is. And you'll notice that it's the outer brain here that has been preserved, plus it doesn't show in this picture, but the brain stem. The brain stem controls things like breathing and temperature regulation, all those other important things. And a lot of the advanced cognitive thinking is done by the outer portions of the brain. Okay, so in this going over Niagara Falls and everything, it turns out the Army and the Air Force really did a lot of studies about what's the limit of the human body. And it turns out, if in this diagram on the upper right, red is acceleration from front to back, and yellow is sideways acceleration, blue is upwards accelerating, and green is downwards accelerating. And human bodies, the red curve here shows you that humans can take 35 Gs of acceleration, 35 times the acceleration of gravity, if they're sitting in a seat and accelerating forward, and they can do that for 0.02 of a second. This is time, the duration down here. But human bodies can take 20 Gs, 20 accelerations of gravity for a full second. And so and in upward acceleration, that's the blue curve here, upward acceleration, humans can take 10 Gs for 3 seconds. So when they design ejection seats from airplanes, they have the person go up, forward and up at about 15 Gs to get them away from that aircraft. And I've undergone ejection seat training. And even in ejection seat training, they only give you a few Gs. And it's pretty strong forces on your body. But the real thing must be something, 15 Gs up and out. But it gets you away from that airplane that's in trouble very quickly. That's right. We had the beginner training, which you sat in a seat and they had like a rifle cartridge, not a rocket motor, that gave you a jerk upward. But these tests were done by one of my heroes, Colonel John Stapp. We'll come back to him in a minute. This tells you what you need to know about jumping off the Golden Gate Bridge. It's about 280 feet down to the water. And according to this study, 99% of the people that jumped off died. You fall 250 feet and you hit it 74 miles an hour and suddenly stop. 85% of the deaths are due to fractured ribs penetrating vital organs like the heart and the lungs. 20% were brain injuries, 27% drowned. I actually had a friend who jumped off the Golden Gate Bridge and survived. She was one of the couple of people who survived. And it turns out she had trained for many decades as an ocean cold water swimmer. And she jumped off the bridge and did not die from any of these other ways. And when she woke up, her body was automatically swimming. And so her unconscious body went right into swim mode and she survived. That, of course, is a call for help. Well, we all know this because of Colonel John Stapp. And here he is. He rode a rocket sled. And in fact, when he did this experiment, he was going 632 miles an hour. And then they ran it into a pool of water to slow it down very quickly. And he set the world land speed record, and then decelerated at 46.2 Gs, and survived. And he looks just fine afterwards. And he's credited with one of the forms of Murphy's Law, which is anything that can go wrong will go wrong, because when they were doing this rocket sled test, they had 8 accelerometers installed to measure the G-forces on his body, and all 8 had been installed backwards. So they recorded nicely the acceleration of the rocket sled, but they didn't record the deceleration at all. And so they had to actually calculate the deceleration because they had done really good video, and so they could measure it from the video. He also tested how much wind. Here he is after all these tests. He tested the effects of wind on the body, and here he is riding the rocket sled with a 570 mile an hour wind, and it bruised his face, but as you see, he completely recovered. And so this way, they knew that ejecting from an aircraft at not supersonic speed was survivable even if your helmet came off. Now this is Captain Brian Udell, and he actually, this is him after he ejected from an F-15 at supersonic velocities. And his face was torn and battered, broke both his legs, broke one of his arms. In fact, his weapons officer who sits in the back seat ejected at the same time and died. So at supersonic speeds, there's the one example we have, there's a 50% survival rate. So when I was giving this lecture, I was asked once, okay, can wind kill you? And the answer is, well, unless it's supersonic, unless it can kill you by blowing things into you or blowing you into things, but straight wind itself, it takes a supersonic wind to kill you. Well, these are just some of the examples from my book, and I'm coming up on the end of my time at 11 o'clock. So I'd like to thank you all for coming, and I'd wonder if you have any questions, because in giving this lecture, I've had all sorts of wonderful questions. So what do you wonder about? So you can tell we tried to give good information in the course of the book and actually tell you about people that had come near to dying in all these many different ways. And we tried to do it in a way that was not too gruesome. I thought the method that surprised me the most was that magnetism could kill you. I was really shocked to discover that there were magnetic fields in the universe strong enough to ionize your atoms. So that to me was the strangest in the book. Yeah, so it turns out if we have our wonderful chemistry lecturer Michael Shaw here, he can tell you about chlorine trifluoride. And you do not want anything to do with chlorine trifluoride, as the name might suggest. It is so reactive an oxidizer that when it touches sand, the sand burns. It catches on fire. And the fluorine fumes themselves are deadly. So there are some chemicals out there that you just do not want to encounter. But that was not the effects of fluorine liquid on your body, and it was just too gruesome So we did not include it in the book. But it is a nice warning lesson. There's a great book titled A Whiff of Death. And it's about early chemists. And early chemists would often smell whatever they were making. And so it took a few chemists to smell fluorine before they discovered it was lethal. So, and I do also recommend Neil deGrasse Tyson's book, Death by Black Hole, and I do love the author of XKCD and his book What If. In fact, in the back of the book, on page 235 in the back of my book, I'm a scientist. I give you links to the best single web page for each of the ways of dying, and I give links to all the books I read that inspired me with ideas for my book. Yeah. So, oh yeah. So, yeah, there are quite a few of these that would be good. Imagine an alien species that could create a strong enough magnetic field to turn you into a glowing human-shaped cloud of plasma. That might be pretty interesting. So yeah, so go ahead, continue living your boring lives, read about these interesting ways of dying. Actually, in Australia, the subtitle of the book is The Science Behind the World's Most Interesting Ways to Die. And I like that better. And of course, when I'm lecturing in England or Australia, I cannot say a billion, because a billion means different things in England English than it does in American English. I have to actually say 1,000 million, which is why I did it in this lecture. So you have to know English in its varieties as you travel the world. And I'd really like to say thanks. Oh, the name of my book is And Then You're Dead. Oops. And in fact, we can bring that back up. So, in fact, here is the cover of the book, which we started with. And it was actually very fun for me. I learned a lot of biology and science, being the scientist behind this book. And by the way, I'd really like to thank the Science Circle, Jess and Chantal, for the wonderful decorations. I love what they found here with the Martian astronauts lying here on the surface, and the chalk outline and the buzzards. I just think that this is the best decoration I could ever imagine for my lecture. Anyway, enjoy the book. Great. I have fun giving these talks. I gave this talk also for the Commonwealth Club in San Francisco, and one 14-year-old in the audience asked the three best questions. And in fact, one of the questions he asked was about wind. Can wind kill you? And so that's when I discovered about Captain Udall, who actually was exposed to supersonic winds. So I do listen to your questions and I learn from them. Oh, yeah. What's the what was one of the funniest ones? Yeah. Um, let me. I'm gonna have to go and look at my annotated book here and see if I can remember some of the funny ones. Of course, the banana peel is definitely funny. Um, uh, oh yeah, so one of the interesting ones that we included in the book that was kind of really interesting to think about was that if you could have a time travel and travel to any other time, what would happen? And it turns out that we live in this window of time on the surface of the Earth when we can live. If you go back 3 billion years, um, there's not enough oxygen on the Earth for you to live, and there's certainly no food yet. So, and maybe then you go back 1 billion years, and now there's oxygen and water to drink, but all there are to eat are algae, and maybe it's toxic even. You go back 100 million years, and you are not at the top of the food chain. You're among the dinosaurs, and you are their equivalent of toast. So there's almost an entire book to be written about traveling in time. If you go 1 billion years into the future, the sun, as it ages, gets warmer and expands and boils off the Earth's oceans. So it's pretty hard to live then too. I think my favorite funny ones were involved thinking of time travel and even going back to our to Lucy, the time of Lucy at 2 million years ago. That you had better be part of a tribe to get protection because those early hominids are so strong they could rip you to shreds. Oh no, yeah. So, um, Ariane, I don't know about Kenshiro. I'm gonna have to look that up. Wow. Yeah. So, and in fact, um, I just gave a talk at the Exploratorium Thursday about the cosmic microwave background, and I even have some demonstrations that help you understand it that I built in Second Life. So maybe for Science Circle someday, I'll actually do a lecture on the Big Bang. Um, my next lecture I want to do is going to be on the force of gravity, and just to give you a hint, we have a couple of gravity probes orbiting the Earth right now called the GRACE satellites. And they're so sensitive they can measure the presence or absence of 1 inch of water on the ground on the Earth anywhere. So scattered over 100 miles, but still an inch of water. And so those satellites were used to look under the ground in California to find out how quickly farmers were pumping water and compare the amount they were actually pumping with the amount they reported they were pumping. And of course, they found out that the farmers were wrong. And so with our new gravity eyes, we can actually look underground and see what's under the ground on the Earth. We've done it on the moon as well, and now they want to launch one to Mars. Yeah, the early history of the human race is interesting. It's recorded in the genome. But I have an expert at work on human evolution. I'm going to have to go ask them, stranger, about that. Oh yeah, I did look at death by volcanoes and nuclear winter, and that chapter on nuclear winter is um, is like what happens in a supervolcano. So a supervolcano can inject enough material into the upper atmosphere to change the temperature on Earth. And we pointed out that a nuclear winter or a supervolcano could lower the temperature across the entire Earth to below freezing for a couple of years, which kills all the. Now, there'd be plenty of wood to burn to keep warm, but food is eventually going to run out. But in terms of the nuclear winter, we point out that cockroaches are quite resistant to radiation. And so you'll probably live in a world of cockroaches. And the only good news about that is that they're quite nutritious. If you're willing to change your diet, you could live from some of the cockroaches that were scavenging after the nuclear winter. We also have a chapter on what happens if you fall into a lava lake. And you have to realize that lava is just slightly less dense than rock. So once again, if you get thrown into a lava lake from a height, it's the fall, it's the stop that kills you. You hit this dense material, splat. And you're much less dense than it is, so you don't sink in it. But it does, the fluids in your body boil and spatter up the lava on top of you. So yeah, don't fall into volcanoes. There have been a couple of cases where people hiking on the fresh lava in Hawaii have broken through the crust and had their leg plummet down toward the lava, and they ended up with serious burns on their leg, but they did survive. It was only their leg that went in. You can find pictures of it. Yeah, we decided on this book not to include pictures, but we do have little sketches. We do have little drawings. But one of the reasons I made this lecture was to gather together some of the pictures to share with you to illustrate the book. Yes, by the way, so a supervolcano can really kill people all over the entire Earth by changing the climate. And more of a local volcano, there's a thing called a nuée ardente, which is a glowing ash cloud. It's a cloud that's over 1,000 degrees Celsius, and it flows. It's denser than air, so it flows downhill from the volcano and envelops you and kills you very quickly. It's similar to what happened at Pompeii. We don't have any of those in the book, although they certainly are a dramatic way to die. One of my favorite stories was in the eruption of Mount Pinatubo. A general who was in charge of the airbase looked out his window and saw a geologist running, and he reported that the geologist yelled at him, "Put some jam in your pocket, General, 'cause we're toast," which I thought was a great way to tell the general that things were going to hell quickly. But it turned out the nuée ardente never reached the airfield, so they weren't toast, and they managed to survive. Okay, so sounds like the questions are drying up, so I will head off and look forward to seeing many of you at Wellstone, my favorite dance place. And thanks for your attention and your questions.